Okay, so I'm going to start the recording. Cool. So for those of you who I haven't met, I am Seth Musser, and I'm giving an inaugural talk on quantum spin liquids. I've subtitled this Disorder and Frustration because we'll see that these are really important features of quantum spin liquids and also a feature of the experimental search for them. Okay, so first of all, just kind of an introduction to the Journal Club. Probably all of you have seen some document with this, but we're really shooting for pedagogical lectures. And I think that means truly erring on the side of over-explaining. I know people tend to assume that everyone else probably knows, like, you know, infinitely much about condensed matter theory, and so they don't want to bore people or insult their intelligence. But it's fine to shoot, I think, for some general talk. And I'm going to be doing that today. I've sort of erred on the side of not being math heavy at all for a first introduction. If you do want to give a research heavy talk, I would encourage you to give a lecture style talk beforehand. So that's next week. I'll be giving a talk which has more to do with my current research in some mean field theory of alpha ruthenium trichloride. But this serves as an introduction to the sort of field of quantum spin liquids. So the talks will be about 45 minutes, and there will be 15 minutes for questions. If you want to give a shorter one, just reach out to me, but probably no shorter than 30 minutes. And as I said, I'm going to be asking people if they're okay with me sharing their recorded lecture, and I'll ask you after the talk you give so that you have a better sense of whether you want that posted publicly. Okay, so Slack engagement. I'm going to create a poll later today with some options for different topics. I think right now, probably I'd like to hear something about Fermi liquids. Some people have reached out to me. They want to hear about quantum Hall states, various weird things that can happen there. And as Ethan and I alluded to, we might want to hear about DMRG as well. So you can respond to the poll and just choose what you think is interesting. If anything is not on the poll, feel free to just post it in presentation options. Okay, so I think that's a sufficient introduction to the club. I just want to thank everyone for attending. Hopefully this grows into something that really is a nice bridge between classes and research. Okay, so let's just start on quantum spin liquids. So first of all, I want to thank Leon Valence because I've really leaned on his lectures at the Princeton Summer School for Condensed Matter Physics. If, like me, you like to watch physics lectures before you fall asleep, these are on YouTube. And there's also this excellent review article that he's written, and I've drawn parts of my talk from there as well. And a bunch of other talks and lectures given by many different people. Okay, so the first question you might ask is, given that this is a talk on quantum spin liquids, what is a quantum spin liquid? And the positive definition is hard because there are many different types. We're going to talk today about some topological quantum spin liquid, kind of the historical example. And we're also going to talk about U1 quantum spin liquids, at least one example of that. But there are plenty more, and they're sort of as varied as the various different metallic states you could have. Okay, so failing giving a positive definition, maybe I can start historically in the absence of some kind of killer example. So quantum spin liquids are introduced by Paul Anderson in 1973, and he has this idea of a fluctuating state of resonating valence bonds. And it has an analogy to a liquid because it doesn't have order. So just like a solid breaks rotational symmetry down to some sort of discrete symmetry, but a liquid preserves rotational symmetry, a quantum spin liquid is a system of highly correlated quantum spins which does not order. So there's no ordering here. On the right, you can see some anti-ferromagnetic order where I have a checkerboard lattice of spins. So this is obviously highly correlated. If I know that this spin is up, it tells me what every other spin is across the whole lattice. But it is ordered and it breaks the symmetry of the lattice. Okay. So if I'm giving a historical introduction, I want to tell you why people cared, or why has this persisted for so long. And initially, people were really interested because high temperature superconductivity was discovered in the cuprate superconductors. And shortly thereafter, Anderson proposed his earlier resonating valence bond state, this fluctuating bond state that we'll talk about today. He proposed that as a potential place to find, or way to find superconductivity in the cuprate superconductors. But we're not actually going to really talk about that much at all, because in the study of quantum spin liquids over their history, there's actually been a lot more interesting things that have been uncovered. So first of all, we have the presence of long-range entanglement. And I'll go through my examples and we'll see all of these types of behaviors. Very interestingly, we have the development of non-local fractional excitations. These are interesting because they don't correspond to any sort of symmetry breaking. Instead, they're really hidden within the constituent particles of the system, just waiting to be revealed or deconfined. And these excitations can have topological statistics. Some of you may have heard about topological quantum computing. And so this is like a big practical reason why one might care about quantum spin liquids. Okay, so historically that's where quantum spin liquids came from, but this is why we care now. And in order to talk about these interesting things, I have to first talk about a boring thing. So we'll talk about order before we talk about this disordered fluctuating state. So many of you may have seen this already, but there's an excellent model which seems simple, is deceptively simple, I would say, but actually is thought to describe the high temperature superconductor as well. So that's the Hubbard model, and we're going to specifically look at half filling to see some kind of boring order emerge. So the first thing with the Hubbard model is we have some electrons which are on a square lattice, and they're allowed to hop, and they have energy T associated with that hopping, and they have energy U associated with repulsion. So this is an on-site repulsion. It's assumed that the lattice is big enough that there's no Coulomb repulsion, which extends further than one site. Okay, so let's talk about the phases here. So if T is much larger than U, there's no penalty to this kind of double occupancy. And so what we're going to see is, oh, that's interesting. Sorry, that unexplored feature of that app there. What we're going to see is a metal. So the electrons will be hopping around here just the way you would normally have in a metal. And this U is just going to act really to renormalize some constants in the band structure. The more interesting case is, suppose instead this term is really large. We want to treat that as the dominant term, the U much greater than T, and we want to minimize it. So that means we're stuck putting one electron per site. And if we ignore this T term, this hopping term, we have a huge degeneracy, a 2 to the n degeneracy, because each of these electrons can be spin up or spin down. That's not enforced by this. We can, however, try to break this degeneracy by considering hopping. So we want to consider second order perturbation theory. And when we do that, second order perturbation theory will take us from the ground state and will apply this perturbation as many times as we need to get back to the ground state. So it should be clear, hopefully, that if I have a bunch of ferromagnetic spins all in the same direction, that if I try to hop, this is not going to be allowed because of the Pauli exclusion principle. However, if I have anti-ferromagnetically ordered spins, I am allowed to do this hopping. Okay, and so this hopping term is going to cause the system to have a preference for this ordered state I showed earlier, this anti-ferromagnetically ordered state. And if you work it out, you'll find that the effective Hamiltonian is the Heisenberg Hamiltonian here. Now, just I guess a little bit of a word, this dot product of spins, classically, this would be the exact ground state. But of course, quantum mechanically, I will have SZI, SZJ, and then some S plus I, S minus J, some term like that, which will allow for these spin flips. So there will be some fluctuation about this state, but this will be certainly classically what the ground state looks like. Okay. And as I pointed out before, this is a highly correlated ground state, but it is ordered. So I promised something interesting, right? Something entangled, something with fractional excitations. So we can ask, what does it actually take to see an RVB, resonating valence bond ground state of the form that Anderson proposed? And we can do a simple sort of thought experiment here. We're going to have the same effective Hamiltonian on the triangular lattice. But now if we think of the spins as these classical Ising spins, it's going to be frustrated. So like I can put a spin down here, and then this spin must be up, but this spin is undetermined in this classical treatment. And so there's some kind of frustration, so possibly we won't just have this boring anti-ferromagnetic state. There is a potential classical ground state, which is boring, and it's just these classical spins, and they're canted at some 120-degree angle to each other. However, Anderson proposed, without knowing which of these was the true ground state, he proposed a totally different one. And here's where we'll sort of start to see some of the really interesting physics. So he proposes that each electron binds into a singlet valence bond with some other electron. And the ground state is just this massive, massive superposition of all these different orders. So here you see I flip these two bonds, for example, and the ground state just looks like a superposition of this. So before talking about the interesting properties here, we want to see if it's actually a ground state. And we can do that just with some heuristic estimates. So we know, obviously, that the dot product of these two spins is going to look like this expansion. We have the total spin here, but that's 0 in these singlet bonds. So for each of these singlet bonds, we're going to have negative JS times S plus 1 as the effective energy per bond. However, or the effective energy per valence bond, rather. But if we want to think about the effective energy per each bond of the lattice, you realize that there's only a singlet bond on a single one of them. So we're going to have to end up dividing by this coordination number. Okay. In contrast, our boring classical state is just going to look like, when I have s dot s, it's just going to look like s squared, and there's going to be some frustration parameter. So in the Ising case, or in the square lattice case, where I have up, down, up, down, I will have no frustration, and x will be 1. Here, I'm going to have a larger frustration because these things can't exactly be 180 degrees to each other. Okay, so if I look at the ratio here, and I prefer to see this interesting state, one thing I can do is make s as large as possible, and I can make x as large as possible, frustrate it as much as possible. So that suggests a possible phase space. So here, again, we're referring to the Hubbard model. As we increase our on-site repulsion, we're going to see more localization of the electrons. And as we decrease that relative to the hopping, we're going to see some metal phase. So in my discussion of the square lattice, at least for my discussion, the square lattice might look something like here. But as we add geometric frustration and the spins become less happy, we move towards this frustrated area, and we might actually see a quantum spin liquid, or this resonating valence bond, this kind of weird state, which we'll discuss the properties of. So if U is much, much greater than T, the triangular ground state is probably this boring classical one. Again, there. So yeah, this boring classical one with these spins canted. But we can try an even more frustrated option, an even better option to see this kind of physics with the Kagame lattice. And that's over here at the right end of the, okay. Well, that's odd. Sorry, figuring out the laser app. That's over there on the right of the diagram. And there's good evidence for a quantum spin liquid ground state from DMRG. But I don't actually know that much about DMRG, so this is my advertisement for there to be some talk. The idea on the right here is you have some fluctuating valence bonds, and you're tuning some parameters to try to get to a quantum spin liquid ground state. But I'd love a talk on more detail here. But okay, for our purposes, if I just want to show you these cool properties and tell you why we care now, we're going to focus on the simpler triangular lattice. It's just easier to make pictures of, and historically, it's what people cared about. So what are the properties? And I just want to remind you of what I said. Some of the things we'll be looking for here are. So we want to see the presence of long-range entanglement, the development of non-local fractional excitations, maybe topological. All right, so the antiferromagnetic state. Is this interesting with these features that I've described? Definitely not. It's just a product ground state. Each of these spins is not entangled with any other, so there's no long-range entanglement. The RVB definitely is going to have long-range entanglement. It's this massive superposition. So not only are the bonds entangled themselves, but I'm entangling the whole lattice, all of these bonds with each other. And I'm not going to go into exact metrics of the measurement of this entanglement, but I hear that Mocking Day has some stuff planned for us later on in the journal club. So I'd love to hear about that as well. Next
Can I
up.
ask a question here?
Yeah, sure.
I am probably trying to apply an intuition that does not really belong here.
Yeah.
But like from spontaneous symmetry breaking, we know that if we have this, so we have this huge degeneracy, right? And the conjecture is that the ground state is superposition of all these degenerate states, which are very different. So why this argument from spontaneous symmetry breaking does not work here? For example, in spontaneous symmetry breaking, people say that, okay, nature will just perform, like, you know, an accidental measurement of one bond or something, and it will, this way it will select one of these states in the superposition, and the system will collapse in one of these singlets,
yeah, so I think that's an excellent question. And part of the reason that people care so much about topological quantum computing is exactly so that this doesn't happen. So like the idea of anyons, you can sort of encode entanglement in the braiding operations of anyons. And you can't destroy that locally with noise.
But is there intuition behind why it is so?
Why you can't?
Because usually because usually in many body systems you don't really have you don't really have superpositions of state at the ground state, right? You usually have something like a spontaneous symmetry breaking, and here there is no such mechanism for some reason.
Yeah, so I think the reason really is that we'll see later that this system is topological. So it has some topological order. It also has these topological excitations. And so any sort of local disorder is not going to break it. But you will see later that these are really hard states to actually find in nature. So, I mean, the vast majority of systems are going to get broken down.
Nice. Thank you. That's a good answer.
Yeah.
I guess there's also like no perturbation that's going to select out one particular state in this superposition.
No local perturbation, you mean?
Yeah.
Okay, yeah.
Yeah,
because in the usual D2 Ising model, you would have a local perturbation.
Yeah,
you know, the example in Weinberg's QFT book is like, he talks about like the Hamiltonian governing like my chair or something. You know, the eigenstates of that are of definite angular momentum, right? And not definite position. But there are lots of perturbations that are like act naturally in the position basis, as opposed to the angular momentum basis. And I guess here it's like kind of the same thing when you consider like if you imagine you being like an observer or something, and like coming in and trying to like break the degeneracy between all the states in the superposition by doing some probe or something. I guess you don't have.
I mean, more than likely, I think if you apply some sort of perturbation to this, you're just going to end up breaking the valence bonds themselves.
Right. I think the easiest way to actually see this is, I mean, look at the diagram you have right now. If you want to perform like a measurement on one of the valence bonds, you might actually break the symmetry between like half of the superposed states.
Yeah, so this is actually excellent because it segues perfectly into the next feature here, which is fractional excitations.
Nice.
Thank you.
That's really good.
Yeah, so, okay. So fractional excitations, again, I want to show you the boring thing and how it doesn't have them. So one type of excitation we might imagine for this boring state is just taking a spin and flipping it. And you might say, well, isn't this a fractional spin, right? This is 1/2, spin 1/2, and I flip it, and that's just spin 1/2. But this is actually a spin 1 excitation because I've gone from 1/2 down to 1/2 up. So it's going to move around the lattice because of this spin flip terms in the Heisenberg Hamiltonian. And that's going to be a spin wave, but it's not going to be fractional. Now, I could try to get more clever, and this is from a paper by Valence. So one thing I could try to do, this is just for illustrative purposes. Obviously, the spins would be canted in reality, but like, let's say I have some sort of quasi 1D system, and I had this antiferromagnetic order. Well, one thing I could try to do is, instead of going down, up, down, I flip and I do a different order here in red. And eventually this is going to have to end on a boundary. And I can think of this as a spin 1/2 excitation. But this isn't actually a good excitation of the system, because this bond is unhappy with energy J. This bond is unhappy. This bond is unhappy, so on and so forth. And what you see is that the number of bonds that are unhappy scales with the length of how much you try to drag them apart. So if you try to actually pull these spin-ons apart, they are going to snap right back. Just like quarks, they're confined. So they are not good excitations. Okay, however, the fractional excitations in a resonating valence bond, as Mockingjay alluded to, are really interesting. You can just break a valence bond here, and then you have your two spins, you can move them apart, and this is going to cost energy J, so there's some gap. But the real question is it actually able to move around? Like, will it be confined? And, god damn it. Sorry. Yeah, it turns out that it can move around. It's totally deconfined, and that's precisely because of the huge ground state degeneracy. We have all these many superpositions, and so for the spin-on to go from this one place here to this other place here, really it's just moving between different sectors of your ground state. You could think of breaking one of these valence bonds at a different place. So heuristically, this is deconfined. We have good fractional excitations here. Okay, are they non-local? Well, the spin-on certainly is non-local because it has to be paired with some other electron in this resonating valence bond state. So I've drawn a rectangle to show that non-locality. But there's also another excitation. So I'm going to be super vague talking about this one because it really depends on the model that you choose to see resonating valence bonds. But it's important to see anionic stuff. So let's just define, there's some kind of thing called a bison. It lives on the dual lattice, which means it's at the center of these triangles. And you draw some sort of branch cut to the edge of the system. You count the number of bonds you intersect, and you choose the parity based on that. So this is a figure from Sashdev. I would think that this would be a charge +1, but it doesn't matter. Like, an even number of bonds here is charge -1. Odd number would be +1. And one thing you see is that this is obviously non-local, but it's also stable to doing something like this. So let's say that I come in and I do some local perturbation of the ground state. What you see here is I've changed my valence bonds, and I'm going to still be intersecting 2 as I go off, because I've broken this bond, flipped it down, this guy's now up. And so I still have charge -1. So that's an interesting non-local excitation, the bison. And it turns out that yeah, sure.
Can I ask another question? Do
yeah.
I have so I have an intuitive picture why Spinon is an excitation, but it's not clear why bison is an excitation, because what is on the right looks like a ground state. So I would expect it to be.
So I was actually slacking with Devanjan about this because this confused me as well. Like, for example, if our ground state is this massive degeneracy of all these different types of bonds, how is it that there's a gap to these type of excitations? And the real answer is that there's just a gap to changing their charge, but also depending what model you use, your ground state will not be all possible valence bonds. It will just be all possible ones you can generate with some certain types of local operations. So I'm not going to get into that, but I will show a slide, 2 slides from now, with a reference that you can check out some model of this.
But what exactly is the claim? The claim is there exist different energies and different states with different energy, but they're all described by like coverings.
Yeah. So I guess the way to think about it is that the Vison is sort of trapped on, or rather the Vison is on this triangle, and it has some charge -1. And if I want to change its charge, that's going to cost me some energy. And I can show you what that might look like. So first of all, these are anionic, which is really interesting. If I take the Spinon around the Vison, I'm going to get a charge of -1. And here I'm going to rely on a specific model known as the Ropchar-Kivelson model and point. And this is subset of these quantum dimer models. And you can check that reference at the bottom there. But basically, so I have an anion here. It intersects 1 based on Soubir's convention. This has charge +1. But you could imagine, suppose I broke this valence bond into 2 spinons, and I move 1 spinon over here, and then I break this guy, and I move, and I break, and so on and so forth, and I make this loop here. What I'm going to effectively do is I'm going to change the sign of this spinon, and so I get that -1. And my question to Debanjan was, why does this cost energy? Because if the ground state is just a superposition of everything, shouldn't this state with 2 here also be in the ground state? Which I think is related to your question, but it turns out that if you're careful, and for this specific model, it does not. Okay, but I think one thing that's clear is that the resonating valence bond can be somewhat challenging to work with exactly. And so we're going to move on to thinking about how we might detect it, and then potentially maybe an easier state to think about. Okay, so experimental detection. Okay, so the first thing you want to do if you want to get a hint of a spin liquid is you want to understand that there's some sort of regime where spin correlations are going to matter and temperature isn't going to destroy them. So your local moments will have some sort of magnetization, and there's a Curie-Weiss temperature. In an antiferromagnet, that's going to be negative. And this is sort of the characteristic temperature of your spin-spin correlations. So as we come below this temperature, we enter into potentially the spin liquid regime. Now for an ordinary antiferromagnet, this would diverge here because we would see ordering into an antiferromagnet, or rather, I guess the magnetization would not diverge, but the staggered magnetization, if we stagger based on the checkerboard, would diverge, and the magnetization would have some peak. So there would be something to indicate things are going on here. But in spin liquid candidates, there is not. Instead, you can usually cool down much lower to some sort of Tn, which is the Néel temperature that indicates some actual ordering of the ground state. So next week, I'm going to talk about a material, alpha ruthenium trichloride, where it is supposedly in this spin liquid regime, and then ordering only happens around relatively small temperatures on the order of single Kelvin. Okay, so that's basically a hint, but that's not super direct. So we might try to do something like inelastic neutron scattering. So in the antiferromagnetic case, this is easy enough. I hit my sample with a neutron and I flip the spin. Then I look at the intensity of the neutrons that come out, and I should see some sort of sharp excitation peak. So omega here is equal to epsilon k, where k is the dispersion of the spin waves. On the other hand, if I split into spin-ons, I'm going to get a broad peak because I have some undetermined momenta here. This can be anything, and that's going to broaden my peak. So I just very briefly want to show a slide of this happening in one dimension. In one dimension, the quantum spin liquids are fully understood, and there's none of this sort of hand waving and, well, maybe that, this or that. You truly, before, I think you may remember my example of confinement, where I had the energy growing linearly. That was because I was in 2 dimensions. But when I'm in 1 dimension, I only have 2 boundaries here, and so the spin-ons are deconfined, and you can reproduce this broad scattering peak very well in experiment and theory. On the other hand, magnons, which are spin flips, have this super sharp dispersion. Okay, but just really quickly, and I guess smooth continuum.
In what other senses is the 1D thing a spin liquid?
Okay, yeah, so I guess I should say here we're going to have bosonization more than spin liquid physics. So I'm really just bringing this up to show the broad peak. Yeah, so this is a better example, or a more well understood example, but we also have one in 2D. Which I think I remember, or yes, I mentioned that it's thought that the ground state of the Kagame lattice has some sort of quantum spin liquid, some sort of resonating valence bond, perhaps like state. And Herbert-Smithite is thought to be an example of that, and it has this smooth continuum scattering. Okay, but I don't actually. I'm not super well versed in this experiment, so I just show this to sort of show some of the experimental features you might look for. If you want to know more, definitely read Leon Valence's review. Okay. However, what if we want to see something like a sharp excitation peak in a spin liquid? Is that possible? Could we do that maybe? So I'm going to use that segue to talk about a U1 quantum spin liquid, just as another example.
Can I ask another
Sure.
short question before we change the topic? So the problem with detection right now is that when we excite our our material, we basically are flipping the whole spin, and we are kind of creating spin 1 excitation, which splits into those spin-ons. So that's our problem, right?
Yeah.
But can one think about I don't know, demagnetizing one of the atoms or doing something that effectively creates 1/2 excitation instead?
That is an interesting question. I don't actually know the answer. So I will, if any of you guys has a good answer to that, feel free.
But did I understand what the problem is correctly? So this is basically.
So this is less a. I think the problem basically is that one of a broad peak like this in Herbert-Smithite, for example, it's not clear that you don't have disorder or something, because it's so broad, there's so little structure, maybe it's just a really dirty sample. And yeah, but I think there are a number of problems with measuring, and each different spin liquid has a sort of killer measurement that you maybe could do to try to indicate it's a spin liquid. So next week, I'm going to talk about Kitaev spin liquids. There, you're expected to get these half-integer excitations, Majorana fermions, which are a fractionalization of a spin. And you're expected to get some sort of thermal Hall effect with half-integer conductance. And so that's the experiment there. I'm sort of using this.
Nice, thank you.
Yeah, sure. This is more sort of as a
And
guide. Sure.
Yeah, that's still a good answer to my question. I wanted to ask, what is the typical excitation spectrum for spinons in 2D? Because in 1D, it's this thing that you just have shown on the other plot, right? But what is it in 2D usually? What would you want?
Well, it really depends on the underlying lattice structure. So all I can really say is that it will be a smooth peak. So you're not going to see.
So it's usually a continuum as well.
Yeah, you're not going to see any sharp peak. Although the example I'm going to give next actually does have a sharp peak, but this is just one quantum spin liquid in sort of a whole variety of them. The field is really broad, so the experimental techniques, I think in Balance's paper, there's like 10 of them.
Good.
But generically, you should expect like a smooth continuum. Okay, so again, I'm somewhat out of my depth here talking about the actual materials and some of the more detailed material physics, but I just throw this slide up to show that when we're thinking about a sharp peak, we can turn to the classical spin ice on this pyrochlore lattice. So the only thing really I want you to note is that there's some sort of hexagonal ring here, and this is going to end up being pretty frustrated as the spins try to decide how to order. So classically, these spins are going to be frozen due to the coupling, and they obey this really interesting rule, which I'm not going to explain, but I guess you can accept this rule. This is a 2 in, 2 out rule. So classically, this almost looks like a divergenceless field. If I associate some sort of line with these spins, then I make loops, and because I have this 2 in, 2 out rule on each pyrochlore lattice, the divergence of this is going to be 0. Okay, so that's pretty interesting because if we're able to actually make this a fluctuating flux lines, then we may be able to see a photon or something like a photon. And that is potentially a route to a sharp excitation. Okay, so also potentially we could have fractional excitations here. So suppose yeah.
Sorry, can I interrupt for a second?
Sure.
In this classical spin ice example, right, there's no any kind of entanglement, whatever, right?
Yeah, exactly. So this is here what we're looking at in the classical spin ice is what Margarita alluded to earlier, where we've just selected one ground state. So we've gone to low temperature and there's been some symmetry breaking, and these guys, like this guy could have been pointing that way and so on and so forth, but they've broken down and they've crystallized into this pattern. It turns out that we're going to need to do something special in order to see entanglement.
Okay.
Yeah. You can also see like potential fractional excitations, but they're frozen in. Because these flux lines are frozen in when we break symmetry and we go to this classical ground state. Any monopole, which has to do with some frustration here where we disobey the 2 in, 2 out rule, and its anti-monopole are going to be frozen. Yeah, so we want to add long-range entanglement. And since we're theorists, we don't care too much about maybe seeing this in the real world, but we can think about the simplest way to add long-range entanglement. And that's just to encourage, if we have some configuration of spins on the pyrochlore lattice, we want to allow them to start flipping around at 0 temperature. And so we're going to add some spin flip term. This is going to encourage a superposition ground state where we actually have a fluctuating magnetic field. And I want to demonstrate that in degenerate perturbation theory, just briefly. Okay, so here's my little tetrahedra. This is the 2 in, 2 out rule. We want to send this to 0, so we need a sum which is 2 positive, 2 negative, and here's our flip. Okay, so I'm going to represent the +1/2 as little dots. Where you don't see a dot, that's going to be a -1/2. Okay, so we're going to treat this term as small. And the first thing we want to do in degenerate perturbation theory is just apply this perturbation as many times as it takes to get back to normal. So we apply one. Yeah, sure.
Quick notational question. What is the spin quantization axis here for each dot? What is plus?
Yeah, so that's, yes, that's a good question. It's the axis which is along, which is coming out of the tetrahedron at whatever location.
But like what's coming out of one tetrahedron is coming into another tetrahedron, right? So like at one of these red dots that's like sharing 2 tetrahedron, how do you decide which one it's for?
Yeah, so the +1/2 is not an actual relation. It's just saying that for this tetrahedron, the spin looks like that.
Oh, that counts as out for that one.
Yeah.
But then if I have a red dot sharing 2 tetrahedrons, which one is it out for?
Then I would have to think up a different notation in order to.
I think we can fix this issue by picking a sublattice for the tetrahedron.
Yeah, that's what I'm wondering, where the sublattice is.
Label on the tetrahedron.
Got it.
Is the lattice of tetrahedra bipartite or something? There are some hexagons.
I'm not sure.
Maybe it should form a diamond lattice, right? I'm not sure about this. But.
Yeah, the diamond lattice is certainly bipartite. Yeah, so I think this is just. Okay, I see. I cycle through the lasers. Yeah, this is really just indicating classically what direction the spins are. And so when I apply a perturbation, this guy is going to be unhappy because it is missing, it needs another dot to have 2 in on this specific tetrahedron. And I can apply it 3 times, and I get some sort of loop around that hexagon I showed before. This is like a ring exchange term. And your ring exchange is going to reconnect those field lines that I drew through the different spins. It's going to take them, break them, and flip them. So it should give us some energy to allow for the magnetic field to fluctuate. And yeah, so really briefly, you can map this using that model that I used earlier. You can map this to an odd compact gauge theory. So the compactness comes because this is 2 pi periodic. And the odd part comes because I am not allowed to have 0 electric field. But this is studied in lattice gauge theory, and provided that this field is small enough, I can get what looks like textbook ENM here. So I should be able to see a photon, and very quickly, this new ring exchange term does allow for propagating monopoles, these fractional excitations, and a photon. There's some numerical work which would say that the photon should be a sharp peak, but it's not seen because the exchange energy is too low. Okay, so again, just to refresh, the quantum spin liquids arose from this study of high TC, and they were defined as this highly correlated spins without order, but that's not really the modern definition. Now we think of long-range entanglement, fractional excitations as sort of hallmarks, and they're difficult to find experimentally. Although that's partially a teaser for my next week's talk, where I'll be talking about the Kitaev model, which is really a brilliant, exactly solvable model that potentially is easy to detect and potentially has been detected. So really a lot of the issues we've been encountering are sort of solved there. And next week, I'll also talk about partons and constructing mean field theories for these spin liquids. Okay, so any questions? I think we have about 10 minutes left. I went about 5 minutes over, I think. And yeah, again, just post any suggested topics in presentation options, and you can ask post-talk questions, or if you are seeing this remotely, just ask away in the Slack channel for questions. Okay. Yeah, that's it. Hit me. Thank you, guys. I appreciate it. Thanks for coming.
Yeah. So can I ask a question about the 3D thing? The spin ice? Blah, blah, blah.
Sure, sure.
So I don't know. I guess I got the impression from the 2D example that like in order to get something that's like not ordered, you want to lock the spins away into singlets, right? So
yeah.
That
that
wasn't.
Yeah, that's only one type. So if I go back, I'm still sharing my screen, correct?
Yeah.
If I go back here, one of these types is the spin singlets. That's the anionic spin-ons, or one example rather of having anionic spin-ons. But you can also have many other examples. And in fact, there's this, the Gutzweiler projection. It allows you to take any type of metal. You can take a superconductor, you could take a normal metal, and you project it and you make it a spin liquid. So there, I was more concerned in this talk about experimental detection and being somewhat connected to reality. But if you don't care about that, you can make any spin liquid state you want, really. They will just all end up sharing this long range entanglement in some way, shape, or form. One good example, Patrick Lee is really fond of this, is the spin-on Fermi surface. So you take a metal, your electrons are hopping all about, they make some Fermi surface, and then you, that Fermi surface is defined non-locally in position space because it's defined locally in momentum space. But if you go to position space, you have this non-local Fermi surface, and you can enforce single occupancy on each site. So you don't have this repulsive case. And what you'll find is you immediately get something which is really entangled and known as the spin-on Fermi surface. This has potentially been seen in some recent experiments where you see quantum oscillations without, in an insulator. So potentially the spin-ons are doing the quantum oscillations and they're not carrying charge. I don't know if that answered your question.
Mm-hmm. Then another thing I wanted to ask was, what is the, I don't know, I guess I normally think of the definition of a spin liquid in terms of like a deconfined gauge field or something like this, but if we're talking about the, you know, no broken symmetries, blah, 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 stuff like this. So obviously you can have a state where you have like some symmetry breaking order that's not related to the spin liquid physics happening at the same time, right? So just because like if I do an experiment or something and I see that there's some type of order at low temperatures, that doesn't mean that there isn't spin liquid stuff going on somewhere, right?
Sure.
So
yeah.
Are there
exactly.
right? But that, okay, so that's a dumb example, right? But is it for sure the case that like I can't have some example where like the degrees of freedom that are participating in forming this whatever emergent gauge field or whatever are not related to any kind of order or something? Or?
So they're not.
But like,
is that not the
obviously,
case? Like would the RVB be an example of that then? They're not necessarily, I think, related to any order.
Yeah, but I'm like, are there examples where you have spin liquid stuff, but the degrees of freedom that are giving rise to the spin liquid also participate in some kind of ordered state?
Oh, okay, yeah, sure. I think you don't mean at the same time. You mean as you cool across?
I think I do kind of mean at the same time. Like,
Okay.
What I'm saying is that if you see ordering in a material, that doesn't mean there's not a spin liquid, because the order could be completely unrelated to whatever is happening.
Yes, exactly.
Right?
Yeah.
So they could be completely unrelated. But are there examples? Is it impossible to find examples where like the order is somehow related to the degrees of freedom that are giving this spin liquid stuff? But
so I think potentially I may be working on an example that would satisfy that. So the idea is basically alpha ruthenium trichloride orders at very low temperatures into this staggered sort of flux state, which is an example of like this ordering without being at the same time as a spin liquid that you gave. But if you apply a magnetic field of about 7 Tesla, you get into probably a spin liquid phase. And if you start applying an even larger magnetic field, you start to polarize, so the spins start to align, but you're still in a spin liquid. So you have some order, which you're enforcing, I guess, as the experimenter, but you nonetheless have a spin liquid.
Yeah. So maybe talking about no order is not really a very
right.
It's not a positive definition of a spin liquid. So
that's why I wanted to emphasize, especially that it's historical. And we don't really think of it that way anymore. I think in Xiaogang's book, when he's talking about spin liquids, he uses this mean field theory construction of the Heisenberg model, where he's like, the expectation of the spins must be 0 in the spin liquid. But we know now that that doesn't have to be the case. So that was sort of the historical thinking, even circa 2006.
Yeah, cool.
Cool. Any other questions?
I don't know. I guess I have another question about so let's see. If you try these kind of Kutzwiller projection things or these part-time kind of theories to construct spin liquids, right? Then you want to have to get a spin liquid phase, you would want to do some kind of construction like this, where you have this emergent gauge field, and the emergent gauge field is deconfined, right? So that you get fractional excitations, right? So I guess if you just think about I want to have this description in terms of emergent gauge field, and I want the emergent gauge field to be confined, then I would think that in higher dimensions it would be easier for this to happen. Like in 3 dimensions, gauge fields tend to confine less than they do in 2 dimensions. But then at the same time, I get the impression that a lot of like spin liquids that people are interested in are either 2D or quasi 2D or something. So is there kind of like
I don't.
What's the role of dimensionality in?
I don't actually have a great answer for you there. I think it's certainly historically, when people were thinking about 2D spin liquids, like we think the high TC superconductivity still potentially could be arising from like a spin liquid type thing. I don't think that's totally ruled out, but certainly there, the copper oxide layers enhance the electron-electron correlation and strength of interaction. And so you're able to get these weird states. So I don't know, my actual expectation would be that the opposite. I think that the lower in dimensionality you go, maybe the more.
I guess it's both, right? You have stronger fluctuations in lower dimensions, which is like preventing order and creating more entanglement and blah blah blah. But it also makes it makes it harder to get deconfined.
Yeah, yeah.
I guess it's both.
Yeah, I
Okay,
think.
I see. I see the floor to other questions.
Hit me.
I have another like dumb question. You mentioned that spinons can be anionic, but in the example that you provided, there was only mutual like Simenon statistic between spinons and bosons.
Yeah.
What about spinons themselves? What kind of statistic they use?
So spinons are fermions with themselves, among themselves, because they are just this 1/2 excitation. But yeah, I think the best way to see that is just noting that they're a 1/2 excitation, so they should be fermionic. In contrast, a magnon, that flip, is going to be a spin 1 excitation, and they actually behave like bosons.
And what is the photon in U1 spin liquids? What kind of excitation is that? Is it?
Yeah, so the photon, the analog of the electric field, when you dot that with the normal that's pointing out of a tetrahedron that we were talking about, that will give you the spin. And so the photon is arising in the electric field there when you quantize the electric field. I feel like
but U1 spin liquids, they don't have any spinons or something like that.
Instead of spinons, they're going to have the monopoles and anti-monopoles. So that's when you're frustrated and you have like 3 in or 3 out. Yeah, so those are fractionalized and non-local as well, because when you start to do that, you'll see that, like, let's say I flip the spin that's happy here. Now I have a monopole in this guy and an anti-monopole in this guy, and I can continue flipping spins until I drag them apart.
Yeah, I see.
Wait, is this so your argument for why the statistics of the spinon is 1/2 because there's
yeah, this may not be very rigorous.
Can't they can have like angular momentum coming from gauge fields and stuff, right?
I'm not actually sure. I think you would know better than I. Presumably, yes.
Well, so I guess it depends on whether when we say spinon we mean. I wonder how.
Can you have some kind of flux attachment, but instead of flux?
Yeah. So actually, yes, exactly.
And then it will change their statistics. Is it what Ethan talking about?
Well,
yeah.
And there's a good picture of this actually in the. I'm still screen sharing. Yes. Okay. So let me move your faces over to the side so I can see. Okay, so what we could imagine doing, for example, is binding a spinon to a bison. The bison is some flux. And if I bind those two guys together, when I swap them, I'm going to get a minus sign, which is going to arise from dragging one of the spinons around the bison. And so if I bind these guys, I'm going to get a fermion. Yeah. So I think the key point I would make about the resonating valence bond state is that if you're thinking about quantum spin liquids in a way which is not historical and where you're actually trying to do some calculations, you should probably not use the resonating valence bond. Like it's usually to tease out some of the more intricate features, it's better to use, I would say, probably the Kitaev spin liquid, which I'll talk about next week. Because there you have the benefit of being able to exactly solve it.
Well, okay, so I know you just told us not to think about representing valence spin pictures too literally, but when you were showing this, I was curious if this is all requires things to be spin 1/2, like if I had spin 1, like I could make I could take 3 spins and make a singlet, right? So maybe there are other.
Yes, so there actually, this is interesting. There's some literature on triplon states, which are
cool.
three spins, and that is, as you can imagine, even more complex. And
this is in spin 1 systems, right? Where
yeah. So I encountered this briefly and considered adding a slide, but then I was like, no, this is too in the weeds.
Well, it seems pathological, right?
But you can look for triplon states if that interests you. I'm sure there's some good literature. Cool. Well, I think probably we'll end it here. But thank you all again so much for attending. And I hope to see you guys next week. And then the week after that, when I think Robert is giving a talk. So awesome. I'm going to stop.
Thanks, Seth.
Yeah.
Thank you.
Thank you guys.